You can think of deep learning to be a subset of machine learning. So deep learning is also a machine learning technique, but we will not only talk about deep learning, but also about some other machine learning techniques. And that is why I changed the title. So what will we be talking about today? So today we will talk about a new framework using which you can solve different types of computational mechanics problem. Now, when I say different types of computational mechanics problem, there are infinite types of problems, and it is not possible for me to show each and every type of problem that can be solved using the framework that I will be talking about. So what I will do is I will talk about something related to inverse problem, something related to fracture mechanics, and then something related to stochastic mechanics, reliability analysis, and those are the things that I will be touching upon. But before I go there, let me first start with the big picture, the overarching goal, what we are trying to achieve. Now, and also try to motivate you that why this is needed with some examples. Now, the talk will be mostly about method, algorithms, how to develop those algorithms. So we will not really see large scale applications in today's talk, but hopefully this will spark some interest for discussion. So, what is the overall goal? What are we trying to achieve? Obviously, we are trying to achieve, or what we are trying to do is model, analyze, and design complex systems, and this comes in different flavors. Now, what you can see on the screen is kind of, you can say that the two extremes. On one end, you might have systems where you have large amount of data, data collected by using sensors, data collected by using cameras, GPS, satellites, and all those things. And on the other hand, you might have systems where data is not available, but we do have some knowledge about the physics of the problem. So if we look into, if we go into these examples, so on the left, what we have is a autonomous car or self-driving car moving around in a city. And for such a self-driving car, you can use sensors, you can use cameras, you can use GPS, and you can use satellites to collect a large stream of data. So data collection is not really an issue for such a system. But if I ask about the physics, what is the governing differential equation that is going to govern the self-driving car? We don't know. So this is a problem where data is available, but the physics is not known. On the right, what we have here is a wind turbine. The wind turbine is rotating, so it is in action. Wind is going past this turbine. And for such a system, data collection, so if you try to simulate this in your computer, it will take days, if not months, to give you result for a single simulation. So data collection by running simulation is very expensive. If you try to do this experiment in a laboratory setting, that will become very costly. So, but you can actually analyze this system in theory from the first principle. So you know the Navier-Stokes equation that needs to be solved. You know the mass conservation law, energy conservation law, and if you are interested in the responses, you know the stress equilibrium equation. So the governing equations are known, but data is not really available. So nowadays, these two domains that I'm talking about comes under two separate domains. On the right, where we have knowledge about the physics of the problem, is known as computational science and engineering, and that is what CSE stands for. And on the left, we have the well-known domain of machine learning. And what are we trying to do? We are trying to develop methods that will allow us to seamlessly travel in this one-dimensional spectra between data and model. So you think of these two examples as the two extremes, and then whatever real-life example you can think of is going to be a mixture of these two. You may have a scenario where you have some data and some modeling information. You may have an example where you have like 70% modeling information and 30% data. You can think of all these cases. And the goal is to develop a framework that will be equally applicable for all these cases, like throughout the spectrum. But obviously that has certain challenges. First of all, cost of data acquisition. So data collection is a challenge. So for example, in this case, data collection is not a challenge for a autonomous car. But for a wind turbine, I talked about it, that you don't really have access to large amount of data because data collection is expensive. Even if you have large amount of data, as in the case of autonomous car, the data will be multimodal in nature. And as a result, it is very difficult to work with such data, which are multimodal in nature. There is a large parameter space. So think about solving a shape optimization problem of a wind turbine blade. You will have to deal with hundreds of parameters, and that is a large parameter space and very difficult to work with. Then no matter what data you have, there will be some missing data, some outliers, and obviously the data will be corrupted by some form of noise, which is often complex in nature. And because of this missing data, outliers, and complex noise, there will be some uncertainty in the system, which we will be interested in quantifying. And last but not the least, can we provide some robust design and control solutions? So can we provide a robust control strategy? Can we design a system which is robust against the uncertainties in the system? So these are all the challenges that are there when you try to develop such a framework. And the question we are asking is, can we leverage recent developments in the field of machine learning to tackle at least some of the challenges that are listed here? So basically the talk that is going to be, so I will be basically talking about machine learning, you can understand, and basically how machine learning can help us in solving computational mechanics problems. So that is the outline, you can think of it like that. But before I go to the core of the talk, so machine learning is a vast domain. So for example, IIT Hyderabad has started a BTech program on artificial intelligence. At IIT Delhi, we have started a school of AI. So AI and machine learning, these are huge domains. There are several methods. So what are we going to talk about? Obviously, we are not going to talk about the whole domain or a subject which is being taught over a semester.